So here is that first one. So it's an integration and it has our base e. So we're going to have to use that integrals of exponential functions rule. But I'm also going to have to use a substitution on this one because it looks like I have a product similar to chapter or section 2. So I'm going to let u be this 0.1 x to the 10th. Because if I take the derivative that with respect to x, I would get 1 x to the 9th. Right? So 10 times 0.1 is 1. Subtract 1 from the exponent when I take the derivative. Well, that's kind of what I have here, 1x to the 9th. If I pull out my 5, I see I have an x to the 9th. So now I'm going to do my substitution. So I have e to the u, because all that is my u. That x to the 9th is my du dx, and the dx's will cancel out, and I'll get this du. So the integral of e to the u is, the integral of e to the u is e to the u, again, plus some c. But I know that my u is 0.1 x to the 10th plus c. So this is the antiderivative of that particular problem. Another one that we had was number 4 that we said we're going to look at. And this is one not using exponential, but using logarithmic rules. So integrals of logarithmic functions, that's on page 376. So this problem is 6 over x minus 5. And so the rules for logarithmics is the integral of 1 over x is the natural log of x. So I don't actually just have an x on the bottom, I have an x minus 5. As long as it's nothing squared or anything crazy like that, if I let my u be x minus 5, my du is still just 1, which I have all kinds of 1's in that integral. So if I want, I could just pull my 6 out. I'm dealing with 1 over. Let's go ahead and say that I have 1 over u. And again, my du and dx, my dx's would cancel out. So I get 6 times the natural log of u plus c. And then my u is just x minus 5. So again, once we have the rules down and we're feeling a little bit more comfortable with substitution, these shouldn't be too terrible. Again, it's just a process of finding the antiderivative, going backwards, which again, I don't know if I mentioned this, we'll actually get to see it, I think, in the last section. Integration, we're just finding area underneath a curve. That is what integration does. We're doing a process right now, and I think in the next section I'm going to show you how Desmos will help you calculate some values. But we're just going through some algebraic intensive process to find antiderivatives, which helps us find areas underneath the curve. So let's look at that last one from section 3, number 8. So this one had exponential functions, and we might end up having to use some logarithmics in this one as well. So again, I have two things that I'm dealing with. So maybe if I did a substitution, let's let u equal 4 plus e to the x. When I take the derivative of that, I just get e to the x. Well, that's good because I have an e to the x up top that I want to get rid of. So I'm going to pull that 7 out and just show you what we have. So the derivative of 4 plus e to the x was e to the x, and that's what I have up top. The 7, the constant I pulled out. So I could rewrite this as 1 over u du, because again my du dx, which is just e to the x, substitutes for that e to the x, and then my dx's cancel out. Don't forget my 7. So I just have 7 natural log of u plus c, but then my u, remember that we did a substitution, is 4 plus e to the x plus some constant. So this would be my antiderivative for this particular problem.